Welcome back to ChemDoctor, and this is the first video in the playlist on weak acid and weak base equilibria. And what we're going to do to start is we're going to compare the acidity of a 1 molar solution of hydrochloric acid, which is a strong acid, with the acidity of a 1 molar solution of acetic acid, which is a weak acid. All right, now, in past videos, I've already defined the definition of an acid and a base, and I've also defined the difference in acid strength versus acid weakness, and these two different categories of acids. The reason that I want to start out with a comparison is because I think it's really important for the student to recognize that in terms of weak acids and weak bases that we're dealing again with equilibrium reactions, and so we're going to be applying the concept of an equilibrium constant, equilibrium position, and so on. So if we look at these two acids, first let's start with the hydrochloric acid. So we can write what we call its acid dissociation equation the following way. So we take the hydrochloric acid, we add it to water, all right, and it's going to ionize to form H3O plus and Cl minus. Now, what makes a strong acid, and I'll go ahead and put a label on it, what makes a strong acid strong is the fact that this reaction goes to completion. So we have 100% ionization, all right, 100% ionization. Another term that's used for this is dissociation. All right, so we have 100% dissociation when this acid dissolves in water. So if we have a 1 molar solution of this, we make a 1 molar solution of hydrochloric acid, we can set up our ICE table for this, or what I call the box, and before we add the hydrochloric acid to the water, this is the situation that we have in the water. All right, we're going to produce this 1 molar solution of HCl. There's going to be 0 of H3O plus and 0 of the Cl minus. After the reaction is over, all right, because we have 100% ionization, hydrochloric acid in this form is gone, right? It's gone to 0 because 100% of this has ionized, and we have produced 1 molar of H3O plus and 1 molar of the chloride in solution. So to find the pH of a strong acid, we literally, all we have to do literally is take minus the log, and I'll write the formal definition first, minus the log of H3O plus, which happens to be the same as minus the log concentration of the original solution of HCl, because it ionizes to 100%. So the pH of this solution is going to be equal to minus the log of 1, which is 0. Now, the whole point why I'm taking you through this will be seen in a second as we look at what happens with acetic acid. All right, now, like I said, this is acetic acid. It's a weak acid. It's also commonly known as vinegar. All right, so you can get this in the store. Now, acetic acid is a weak acid, and that means that it does not dissociate to 100%. So I think we'll go ahead and put that here. This does not ionize to 100%. All right, it's going to ionize to a much smaller fraction. So, like with the strong acid, though, we can write its ionization equation this way. So it's going to undergo a reaction with water. All right, and it's an equilibrium reaction, so I'm going to have my double half arrows here, and then we're going to be producing H3O plus the anion C2H3O2 minus. Now, before we get any further, I want to emphasize a couple of things here. Going back to the HCl, and I defined this concept in earlier videos, but I'm going to underline in the HCl the conjugate base. All right, so every acid has a proton, right? So here's the proton that's going to be donated to the solution, and I've underlined the conjugate base, which we see again here. And water, in terms of the strong acid reaction, is operating as the base, and here is the conjugate acid. Now we have a similar situation with the acetic acid. I'm going to underline it here. So in acetic acid, this is the conjugate base. Okay, here is your proton that's going to be donated. Water is operating as the base. On this side of the equation, here's the conjugate base of the weak acid, and here is our conjugate acid. All right. Now, acetic acid in water is an equilibrium reaction. It's not going to ionize to 100%. It's going to donate this proton to a much smaller extent. And like with all equilibrium reactions, all right, we have an equilibrium constant, which I'm going to define as capital K, and then we're going to have A. And the subscript A simply means that this is the equilibrium constant of an acid reaction. All right, and the equilibrium constant will be equal to an expression like the other equilibrium reactions that we've looked at, which is essentially going to be the products divided by the reactants. So it'll be concentration H3O plus times concentration of the anion divided by concentration of the acid. Let me just clean that up a little bit. Sorry about that. So we'll get in here. All right. So HC2H3O2. All right. Now, the equilibrium constant for this particular reaction, the Ka for the ionization of acetic acid, is 1.8 times 10 to the minus third. So the first observation that you can see here relative to the equilibrium constant is the fact that we're dealing with a small value. All right, and reminding students of the thermodynamics in this, that means that the delta G for this reaction is going to be a positive value, and it's probably going to be somewhere between 20 to 50,000 joules. The fact that it's a small equilibrium constant, what that means is that when we get to equilibrium, the concentration of reactants is going to be much greater than the concentration of the products. All right? Now, with all this said, then let's go ahead and calculate the pH of this solution. So we're going to set the reaction up the same way that we did for the strong acid. We're going to have our box or ICE table, and before any reaction we're going to have 0 of the H3O plus and 0 of the acetate or the C2H3O2 minus. The water doesn't matter here because it's a pure liquid and it doesn't appear in the equilibrium expression. After the reaction, this is going to be 1 molar minus X, this is going to be X, and this is going to be X. In a lot of respects, setting up the equilibrium expressions for weak acids, and you'll see later the weak bases, is easier than a lot of the expressions that we're used to working with at this point, because the stoichiometry is usually more straightforward. Like you'll notice that in this reaction everything's 1-to-1. So now, setting up our expression, it's going to be x squared over 1 molar minus X is equal to 1.8 times 10 to the minus fifth. Now, since we're dealing with a small equilibrium constant, we get to neglect the X. So the expression is going to simplify down to x squared over 1 molar is equal to 1.8 times 10 to the minus fifth. And going ahead and solving then, alright, so it's going to be x squared is equal to 1 molar times the 1.8 times 10 to the minus fifth. And then we're going to square root both sides. The point is that x is going to equal 0.00424 molar when it's all said and done. And this is equal to the concentration of H3O plus, and it's equal to the concentration of acetate, since the stoichiometry is 1:1. Now notice out of the gate here that 0.00424 molar is way less than 1 molar. Alright, which is what we had over here with the strong acid, because it ionizes to 100%. So the amount of hydronium or H3O plus that we're forming in this reaction is significantly less than what you see with the strong acid. So I'm going to pull this over here, and now what we're going to do is we'll calculate the pH of this solution. So the pH of the 1 molar solution of acetic acid is going to be minus the log of 0.00424 molar, and this is going to equal, so it's going to be minus the log of 0.00424. Alright, so the pH of this solution is going to be 2.37. Alright, and correlating this again with the strong acid, look at the difference. Alright, the strong acid was pH 0 for a 1 molar solution. For the weak acid, with an equilibrium constant of 1.8 times 10 to the minus third, we're at a pH of 2.37. This is the reason you can eat vinegar and you cannot eat hydrochloric acid, because the level of ionization is so significantly different. The hydrochloric acid is going to dissolve your esophagus. The vinegar is going to taste good if you like tangy dressings, and it's essentially going to leave your esophagus alone. Now the last thing that we're going to do is we're going to calculate what's called percent dissociation, which I'm going to call percent dis, and this is going to tell us the level of ionization. It's equal to the concentration of H3O plus at equilibrium over the concentration of the weak acid, which I'm going to call HA for short, initially, which we'll put a naught here to mean that. So the naught means initial concentration, and then this is times 100. So if we calculate the percent dissociation for the 1 molar solution of acetic acid, it's going to be equal to 0.00424 divided by 1 molar times 100. And what we get is percent dissociation is going to equal 0.424%. So literally, when we add vinegar to water, and we make, let's say we make a 1 molar solution, the level of dissociation is only 0.424% versus 100% for the strong acid. All right, and what this means in real terms is if we go back up here and we calculate the molarity of the acetic acid after it has dissociated, all right, it's literally 0.996 molar after the solution has ionized. All right, and I'll just add in here to finish, both of these concentrations were 0.424 molar. All right, and with that I'm going to go ahead and close the video.